This is 1 hour, and this is 555.
You think there will be people be on time?
I hope so. He's saying 14:30. And then in Turkey, because they're looking for a home for the girls. And there are 6 or 7 hotels, right? So at least one can come out.
Do you have any medications? No. And they go through the document so many times. Like you still
Anyway, I want to ask for a strike, a gym strike, and a minute taker.
Now?
When you will pass. We ask somebody, I don't know.
Yeah, awesome. Our lives are
Point that you get from let's say that items here, but it's not unusual that the farmers are coming from Latin America. We assume that if you're coming from there, you're smiling something. I don't care what.
Hello, welcome. You've ended up in Opsec in a not so small room, but we don't have such a big audience, so it's a perfect fit. So first, some administrivia here. So before we can start, it would be nice to actually have a Jabber scribe. Anybody willing to look into the Jabber things and actually relay questions if there would be any?
And somebody is sitting in the typical JavaScript seat.
If I get on
Thank you.
Thank you.
And
Now-
minute taker?
Yep.
I can do offline if you want. I'm not going to be able. But if you want, I can do with the recording.
No, what?
Would be nice to actually have like live if that is possible.
Okay, I'll do.
Yeah. No volunteers from the audience to take some minutes. You don't have to do it alone.
I can do it from the recording, but I don't have my computer with me.
Okay. So we have 2 volunteers for the recording then. Okay. Thank you. So the next thing is, as you have seen, probably there's like a new note well out here. If you haven't seen this thing, you probably haven't been going to the sessions and just been enjoying the social, which is maybe not the intention. So take it into account. Be aware of any IPR. If you have any IPR and things, and you don't want to disclose, don't participate. So in that case, you probably wouldn't have seen this note well anyway. So the book sheets are going around, fill it in, so that next time we get like, the appropriate size room and we know who actually has been here. So that's really good. And in addition, if you don't fill it in, we actually get like a grumpy face from our area director, and we want to avoid that. We want him to be a happy face.
Can you speak up, please?
Yep, I can do that. Perfect, sorry. So for the agenda today, we have carved it up in 2 different sections. So we first are going to be discussing some of the working group documents which had some activities upon them, and see how we can progress them, towards further completion. Now, in complement to that, we also started like a couple of IETFs ago to discuss some operational security, aspects which do not really have working group documents at all, but are in the general interest from from a security perspective for like a wider audience. So we're trying to group those things here in this particular working group here. So we have found 4 different topics here, which had some activity during, before the last IETF and this IETF here. So that is what we have the agenda at this point in time planned. Now, before we start, anybody, would like to do some agenda bashing or like make some changes or something like that? If that is the case, now is your moment to speak up. Okay. Then a very quick work group status here. So we actually haven't published, and you'll see since the last IETF meeting, we actually have like 2 active working group documents, which we're going to be discussing here. And we actually have like 2 individual documents which had like some further activity here. For the rest, little activity on the email list, as you have seen also. And that is the current working group status at this point in time. Now, before we actually get started with Fernando with this draft here, so one observation I had is that I went and actually had a look into the working group alias, and also into the document itself. And while the document, it is looking, reasonably good in my eyes, I have noticed that there is like not a lot of discussion on the working group list on this document. And also did like a search. I found like 5 emails, on the list on this particular, this particular draft. 4 of them were like, I've updated the draft, and it's like a new version. So only 1 active, feedback comment or something like that. Now that is surprising to me. So it makes me wonder, is this document doing the right thing? Is it actually tickling the interest of the working group? And like I said, when you look through the document itself, it is actually, quite well written, and it seems, in my eyes, it's touching upon the right, elements here. So I'll be looking feedback upon that also later on from the audience, and I'm pretty sure that Fernando is also, looking into that aspect also, and it might actually have some feedback. So, want to say something else? Okay. Then let me jump to the first. You have a clicker thing also, eh?
Okay, cool.
So you can stand into the ping box. If you're bigger than the ping box, yeah, you should.
We'll be doing a quick overview of this document, recommendations on the filtering of IPv6 packets containing extension headers. Essentially, as a summary about the document or what this document is about, it's essentially an IPv6 version of 7126. We was talking about IPv6, IPv4 options. And essentially for each extension header and each IPv6 option, it tries to summarize the security and the operational implications. Like security, what can go wrong if you actually allow packets with those extension headers or options. And operational implications is what happens if you happen to drop those packets, okay? The idea is that this document provides operational advice on how to filter packets containing these extension headers at transit routers. At some point in time, the discussion was about how to filter these packets everywhere. But there was quite a lot of discussion about that, and essentially the agreement that we got to in the working group was to make this document focus on transit routers. The idea is that there the approach should be more of a blacklist approach, as opposed to what you do probably at the edges, where it would be more of a whitelist approach. Okay. The hopes, you would say, depending on your point of view, is that these might help improve the situation in those cases in which you have transit systems that are dropping packets containing extension headers, or at least raise awareness in those cases in which those packets, are being dropped, and let's say the security or operational considerations are not considered. What are the changes that we applied to version number 3? Essentially, just editorial comments. And there were a few sections that had missing contents. So we have sections for some specific options. Some of them might have been like experimental, or for protocols that at least we were not that let's say familiar with. So it was a matter of digging into the corresponding specifications, and try to figure out what the security implications were, and what might break if you were actually to drop the packets containing these extension headers or options. That is essentially it. So a discussion that we have among us co-authors was that you might have seen that recently the revision of 2460 was published. Okay, so then there was the question, and there were some things, particularly when it comes to, for example, hop by hop options extension header. There were some, let's say, modifications or some changes in 2460 in that respect. So the question here was, well, what to do about it? Like whether, we just reference 8200 and focus on that one, which is supposed to be the current P6 standard. Just do it on 2460 or both. From our point of view, we should probably do both because, well, most of the, you will have lots of what you might call legacy implementations, which are most implementations that are still behaving as in 2460 or, in theory, according to 2460. And, in the near or long term, you might have, implementations behaving according to what's in 8200. I don't know if there's any input or you have any thoughts about that. I mean, by default, if you don't complain, we would be doing both, right? I mean, considering what's the case according to 2460, and also, what changes according to 8200. Other than that, yes.
So maybe just to help you, what we can actually do like a small hum in the room to actually see where most of the feeling goes about. So I'm going to do like 2 hums. The first one actually is to keep it on the original one only, correct?
On both.
Yeah, I mean, we essentially have like 3 options: doing 2460, doing 8200 only, and doing both.
Let's then do yes.
Ron Bonica, Juniper Networks and co-author. For folks who aren't IPv6 people, maybe it would be a good idea to talk about what actually changed in the hop-by-hop specification in 8200 so they'll know what they're humming about.
So the idea, as far as I remember, was that in theory, I mean, that means according to what 2460 says, if you receive a packet that has a hop-by-hop options extension header, it has to be like, sent to the slow processing path of the router to actually check what's inside the, hop-by-hop options extension header. Obviously, that's bad for a lot of reasons, performance, and obviously, as a result of that, you can get denial of service attacks. And as far as I remember, what Sixman agreed to was that behavior would only happen if you actually have a reason or if you are expecting something to be in, the hop options extension header. I guess if you have deploy RSVP or something like that, that's the only case in which you look at the packet, but by default, you wouldn't look at hop options.
Ron Bonica, again, more specifically, unless you've configured the router to process hop-by-hop options,
Exactly.
you'll just pass them without looking at them.
I mean, the thing here is that, so you have what 2460 says, what 8200 says, and what implementations we're actually doing in some case, which was like ignoring that anyway. So in the current version of the IDE, we already discussed what implementations do and what 2460 says. And I guess that 8200 is essentially reflecting what was already happening in practice in many cases.
So Warren Kamari, it seems like the additional text you'd have to add is really small, like maybe
Yes.
just saying routers already do this anyway. So that seems like a trivial change.
Yeah.
So in that case, maybe the hum not needed and just do it.
Cool.
Okay.
Also make a comment on the working group last call. It would be cool if you could CC that to V6 Ops, or maybe just send a copy of the draft now and be like, hey guys, you might want to look at this because they might have useful notes.
We did, I think Gunter did at some point, and there was, I mean, let's put things this way. So there was some folk complaining that we were essentially encouraging people to drop anything that had extension headers. That's not what this document does. Actually, is to put it in some way, it's way more permissive than what I personally do, so to speak. From the author's perspective, I guess after that small change, this one should be ready for working group last call, from our perspective.
Okay. So just, how many people actually in the room did actually have a look at this draft? It's quite a fair number, actually. So how many of those who actually have, looked or read the draft, feel this document actually is ready for the working group last call?
It's not that I don't think it's ready, it's that I don't remember enough.
Okay. Okay. Should we? Yeah. I think, so like I said, there has not been like a lot of discussion on the group on this particular one, and one of my hopes actually here is that the working group last call actually triggers people to actually go and read it, because otherwise nothing will happen on this. And like I said, the text in this document is already quite well written, so I think it's ready for the working group last call. So
Cool.
I will do this after the IETF.
Cool.
I think that's it.
Thank you. Marike. You have no slides, huh?
I have no slides. It's great. Actually, I was trying to create some slides, and then I realized that would be kind of difficult. So I just want to give a status of the document. So this document was started actually by all three co-authors back in 2012. And the premise was that if people were starting to build IPv6 networks, when they have to think about security, what are the security considerations, and also what are the recommendations that we can give overall. And basically the premise was that we would look at all the documents that had security somehow embedded into any of the v6 documents and make it easier for people to understand the security recommendations. 5 years later, right, it's turning into one of these projects where we know that will never absolutely be done, because there's always going to be continuing work, like with what Fernando was just presenting, and we want to add all that. We had a last call this past May, and there were a lot of really great recommendations. I also, well, the authors, we know a bunch of V6 operators who don't necessarily participate in the IETF, and we requested for 5 or 6 of them to do a thorough read, which they did, and they also commented some very good comments. So in the last 2 months, I mean, it'll be at least 12 to 18 hours worth of work, literally, to really incorporate all of them, look at them, parse them. So as authors, we've decided that we really want to do the diligent job to make sure that the current state, as it's represented now, and from all the comments that we got, that we're actually seriously going to look at what should we embed, and then also bring to the working group anything that's controversial, so we can make a decision. And then hopefully by the next IETF, we can have a last call where we can declare the document done in its current state. There was one conversation about ULAs and NAT66, and a recommendation that there be very strong language in terms of do not recommend. And while the answer that I got when I asked, because last year I had a hiatus for a year for personal reasons, but I said, yeah, there was a lot of discussion and there was text. And when I said, can I have a pointer? There was silence. So I actually read through all of the comments there were from last June and July. I found the text that was embedded in 2 different comments. So now I have that reference, and we're going to be discussing how we'll incorporate that. And so that's basically the status. And then hopefully we'll have a next rev out in the next couple of weeks, just so that we can get to finalizing it. So any questions? How many of you have read it? Cool.
Mike?
Fernando, is there anything specific that you remember that was controversial? That you mentioned there might be some controversial stuff.
I just remember that there were some competing comments from different people as to what the text should say. And so those are the things I didn't have time to put onto slides, because quite frankly, we had really good comments from about 10 people. And there were 6 of them that they sent it to my personal email, because they don't contribute to the IETF. And so, but they're operators, and we did want their input, because this is for operators and considerations and operational environments. But one of the things we're going to do as authors is to write down basically the recommendations or the comments that we got, so there's visibility to this entire working group, even the comments that we got in private.
Natalie Treneman, RIPE NCC. I would like to first thank the authors for this document. We as RIPE NCC are currently almost finishing up the build of a new IPv6 security training course. This document has helped us greatly in making things understandable for operators and on how to move on with IPv6 security. So thank you.
Great, nice to hear. All right, that's it for now. Thanks.
Thank you. So next speaker is Joanna Ilrich. She is a researcher in SBA in Austria. It's not about the draft, but it's also her first IETF here. So she's a security researcher and work on IPv6. I think it was nice that she present what she's doing right now at SBA.
Thank you. So it seems like I'm a bit smaller than the average speaker, but now it's fitting. Thank you for welcoming, quite warm. So the intention of the document that I'm presenting, it's a paper that was published at the scientific workshop, was more or less similar to the document that was presented before. When I started to work and I was told to collect all things that are related to IPv6 security and attacks and countermeasures. And back then, when I started it, I just looked it up. It was about the same time when you started with this draft. So same idea at multiple places. I started to collect it. And at the first, were a lot of personal paintings by hand. And afterwards, I started the systematization of them. And as the time it takes to go through a lot of attacks, I will give you an idea of what I did and why it could be beneficial for you. And beneficial also beyond the document we discussed just a few minutes before. So what I did after collecting all the things, I was classifying according to some general language that describes attacks by the here mentioned classification attributes. The intention is that you get an overview of what a specific attack does on a quite high level, what is done and what are the results. What may also be for interest for you here, it's distinguished between security and privacy issue that arise from configuration, so that is more towards the operators, from design that is more for standardization, and implementation, so for the people writing code. So just that you see or get an idea of what I did. So these are the action that can be done in an attack. I don't want to go in it in detail right now, but the results that I got are a whole bunch of tables, and they are on purpose now quite small, so don't try to read them, where these attacks got a number and a name and are classified according to this. And there are even more attacks, and there is a third table where the countermeasures that help to a certain extent got a tick with the respective attack. What also sometimes happens that a countermeasure occurs again at the attacks of the left side, because sometimes countermeasures introduce a new attack vector. Like, for example, the privacy extensions saves your privacy on the one hand, but on the other hand, it can be used as a covert channel, for example. Whether this is harmful or not depends on the use case, but there's potential to use it that way. So what are the benefits for you? One thing is it can be a good introduction to IPv6 security. You might be the expert, but there are maybe some non-experts outside this room. And I think these tables are still a good overview to get an idea what's going on, and it's 11 pages of reading, including references, so you can do it in 1, maybe 2 hours. The second thing is it's a good overview and the common ground for discussion, because sometimes I read something and I don't, and there are multiple attacks in this area and you don't know really what the other one refers to, so it might also be helpful for that. And a checklist for whatever you needed. For example, penetration tests, or whenever you implement and use new stack or whatever, you can at least check against the list whether you considered this or not. The document is, as I told before, also a little bit older, and back then I saw 3 challenges, which was securing the local network, which is more or less the SEND protocol, which is specified but not used, but it's another story. Then there's reconnaissance, which I work also a lot. For the people that are interested in that, I can recommend MapRG tomorrow, because there are some people who had similar problems in scanning and doing large-scale measurements than I did, because ICMP is largely rate-limited at routers. And the addressing stuff, there is on the one hand the idea of 7217, which is now there, which wasn't back then when I wrote the document. And I also saw that there is a revision of 4941. So this was also not back then. But I might add a new challenge where I don't know yet, and just want to pose the question in here, whether this should be issued here or by another technical community. The European Union is focusing on new privacy legislation in May 2018, and it will also be important for all companies that offer services to European citizens. So also a lot of, for example, US-based companies will have to adopt. And the thing that is especially outstanding for the IPv6 community is that now it's clear that IP addresses are considered personal data, and if they so unique that you can refer back to the respective person, that you have to treat them quite strictly according to the data protection rules. So you're not allowed to collect them more than necessary, store them more than necessarily, and so on. The only way to kind of get beyond this is some level of pseudonymization. And for example, you might consider privacy addresses as such a kind of pseudonymization. However, the addresses are stored at another entity, usually, for example, at a web server, and the addresses are assigned at a client somewhere. And web servers should have a log usually. This is good security practice. And there, if the server would have to decide whether this is a unique address, in the sense you can refer back to the person, and then it has to apply the strict rules or pseudonymize it some way, or if it's a privacy address, he can save it as it is, for example. And I don't know, or at the moment it's quite unclear where's the level, when is pseudonymization enough and where not. And the question is rather whether the technical community should give some guidelines about that or have some ideas about it. Thank you.
Thank you. Any questions for Joanna?
No, I just want to thank you for this work, because I think it's really important for the community, and especially spending all that time collating everything. So thank you.
So, Kotuki, are you here? Okay.
Thank you. So good
Yeah,
afternoon.
Lutica here.
Good afternoon. So this work started back in November, just before Seoul, Korea. The 00 draft was published at that time, and Opsec didn't meet in Seoul. So this is the first time I'm presenting it in Opsec. However, it was presented in GROW in Korea. And there was a whole lot of very good discussion on the GROW list, some of which was also copied to Opsec list. And that discussion benefited the draft greatly in terms of revising it from 0.0 version to the now 0.1 version. So thanks to everyone who commented, made suggestions, and so on, mostly on the grow list, but some on the Opsec list also back in November. So the state of things with URPF, as I'm trying to summarize it here in this slide, strict URPF is usable in very limited circumstances, particularly when the ISP has a directly connected customer and has a complete view of the prefixes that the customer originates. Strict URPF is very straightforward. Loose URPF is good to use when ISP is filtering on all the, like the entire BGP table that it is receiving from an upstream. Primarily, what is being filtered on is bogons and such. So it is useful to filter those out, but otherwise it's not very effective for IPv4 address spoofing. So that's why BCP 84, which talked about URPF, all these different flavors of URPF, it put some emphasis on feasible path URPF, which is a refinement over the strict or the loose. So basically, ISPs are apprehensive that they may be denying legitimate traffic from their customers. So if they did strict, that could certainly happen. If they didn't announce the prefixes to the ISP, but they still send data packets with source address in those prefixes, then the customer's traffic will be dropped, and ISPs are afraid to have that kind of a denial of traffic for their customers. So feasible path tries to fix that. Mainly, it depends on the recommendation that is made in BCP 84 that if you are a customer announcing your prefixes in BGP to your transit provider, make sure that you announce all your prefixes. And if you are doing traffic engineering, put some ASS prepend with your own AS multiple times so that you can achieve traffic engineering if you are multi-homed. However, you should announce all your prefixes to each of your transit providers. By doing that, although the ISP's AS may not choose all your prefixes as best path, all the prefixes that you announced as their best path, at least they have heard from you that these are the prefixes that you have and you have sent updates to them. They will incorporate that in the RPF, the reverse path filtering table, and as a result, they'll be more flexible in terms of the source address validation that they do. So that's the idea of feasible path. Even though feasible path supposed to work that way, many times the customer ASs don't announce all their prefixes. They omit some of the prefixes. For traffic engineering purpose, certainly they are announcing different prefixes to different ISPs. So there are scenarios we look at where feasible path fails, doesn't perform as you would expect it because of the behavior in terms of the announcement of the prefixes in BGP. So we will look at some examples. And we are looking in this work, we are looking to propose an improvement on feasible path URPF, and we are calling that for now enhanced feasible path. And the purpose of all this, or the goal, is to encourage a wider deployment of URPF or BCP 84. The key principles of this algorithm can be summarized in these steps. First of all, the ISP router, it's receiving BGP updates from the customers, from peers, from providers. So it can look at the collection of all the BGP updates it has received. It creates a union of announced prefixes that have a common origin AS. So that is the key here. So create a union of prefixes that all have a common origin AS. So once you have done that, and as I said, those announcements could have come from a customer, peer, or a provider. So once you have done that, you take that union of prefixes and look at the interface, for example, towards a customer, and the customer has announced at least one of those prefixes. Now you give the benefit of the doubt to the customer, to that interface, that since this prefix with that origin AS came in a BGP announcement towards me, I'm going to allow in the source addresses this prefix. So any address in this prefix is good. I'm going to accept. And then you give the benefit of doubt by saying that I noticed that these other prefixes that I heard maybe from other interfaces, they share the same origin AS as this prefix. So they are all originating from the same AS. So potentially they all have a BGP update path towards me. If they're going to send eventually later, if they're going to send data with source addresses in those other prefixes, potentially they could have also announced BGP, their BGP announcement could have made its way to me. So you give them the benefit of doubt and expand your RPF list by saying that if I saw one prefix with a particular origin AS, and if I have in my table other prefixes which this interface didn't announce to me, but they did come from other interfaces and they have the same origin AS, then I'm going to give the benefit of doubt and be more flexible in my URPF. So that's the key idea. And by doing this, they can choose to apply this not across peer and provider and so on. They can choose to limit this algorithm to customer interfaces. So some scenarios through which we can walk through how this functions, or how some of the URPF techniques fail and how some of them do better. The first scenario is pretty straightforward. AS1 has two prefixes. It originates. It sends P1 to AS2, announces only P1 to AS2 and only P2 to AS3. And AS2, AS3 exchange those prefixes between them. So the reachability is there. AS2 has reachability to P1 and P2, and AS3 has also reachability to both. So that is there. Clearly, in this case, strict URPF will fail if data packets were to go from AS1 with the address in P2 towards AS2. AS2 has not heard P2 from AS1. So AS2's strict URPF will say, no, this is not allowed, and the packet will be dropped. So strict URPF would fail. Feasible path URPF would also fail since P2 was not announced to AS2, P1 was not announced to AS3. Basically, AS1 didn't follow the recommendation, operational recommendation in PCP84. It is supposed to announce all its prefixes with prepending if preferable and so on for traffic engineer, but it didn't. It only announced prefixes selectively. So feasible path URPF also fails. Loose would work, but that's not what we desire to have. Enhanced feasible path works best because what AS2, for example, is saying that I heard P1 directly from AS1, I heard P2 via AS3, I see that they have the same origin AS1, therefore I'm going to allow source addresses in P1 as well as in P2 from AS1. And AS3 does the same thing, and there is no denial of traffic for the customer. So one scenario where it works good. Even if you have prepending, so now AS1 is trying to follow BCP84 operational recommendation. It announces all its prefixes to AS2 as well as AS3, both its transit providers. And it does prepending in order to achieve whatever traffic engineering it wants to achieve. Now AS2 and AS3 are in the happy position that they know all their prefixes that the customer has, and it has announced them in BGP. So their strict URPF works, would work fine, yes. And as far as now, we are looking at comparison between feasible and enhanced feasible. As we go through the examples, we try to highlight the fact that the feasible may fail sometimes, but the enhanced feasible still works. That is the improvement we are trying to show. So feasible path works if the customer route is preferred at AS3 over the shorter path. So that is, if that happens, if the customer route is preferred, then it works. If the customer route is not preferred, instead the shorter path through a peer is preferred, then even feasible URPF will have a problem. Not on this link. directly uplink. But on the peer link, if a data packet goes from AS1 to AS3 and shows up at AS2, and AS2 happened to choose best path, not its right. If it didn't choose the customer's route as the best path, then there could be a problem with the feasible path. Otherwise, not. Regardless of the type of path selection that AS2 or AS3 do, enhanced feasible path works in both cases, whether the customer prefix is preferred or the peer shorter path length is preferred. In both cases, enhanced feasible path URPF works only because of the simple rule that if it's the same origin, I'm going to give the benefit of doubt, right? We explained that before. This is a little bit more complex scenario. So unlike in the previous scenario, in this scenario, we are back to the case where the customer is not observing the BCP 84 recommendation properly, announcing different prefixes to different upstream providers and not announcing all its prefixes, so selectively announcing. So only P1 propagates from AS1 to AS2 to AS4, only P2 propagates from AS1 to AS3 to AS4, and P2 also propagates via AS5 to AS4. Now we're looking at AS4, and what we want really is that the flexibility that if AS4 is seeing data packets with source addresses in P1 or P2 on any of those interfaces, whether it is from the two customers below, AS1 or AS2, whether it is from the peer, AS5, in all cases, AS4 should be willing and ready to accept data packets originating from AS1 with source address in either P1 or P2. And that happens. That happens with enhanced feasible path alone. We are kind of putting aside loose URPF. In this scenario, that doesn't happen with feasible path, but it happens with enhanced feasible path. Once again, because of the flexibility of giving the benefit of doubt based on the same origin AS. So the basic idea is that if P1, I got an update from P1, that is good because I saw the BGP update from P1, so data packet with source address P1 is good. P2, same origin AS, so potentially there is a data path for P2 as well, so I'm going to accept it. They both have the same origin. Good. So now in the GROW discussion, it got, pretty interesting. So multiple people, Job and a couple of others, they came up with the same example to show one case where it wouldn't work. And that is shown here, the example they shared on the GROW list. And essentially, what it says is that AS1 puts a no export. So P1, P2, it announces both prefixes to its upstreams, to the two upstream transit providers. It does. But it puts no export in the two updates towards AS2. So in this case, AS2 has not sent those P1, P2. It has not propagated them to AS4. So AS4 now does it on this link from AS2 to AS4. When a data packet shows up with address in P1 or P2, AS4 has no clue because it didn't hear any update at all regarding P1 or P2 on that link. And therefore, if a data packet shows up, no matter which flavor of URPF is applied, it's not going to accept those updates, data packets. So because it didn't get any updates, so it doesn't even have the ability to sort of do some calculations in all the BGP, look at all the BGP updates and provide some kind of a tolerance or generosity. It can't do that. So feasible path also doesn't work. So I'm hoping that these scenarios are like not very frequent, but the key idea is that if there is a place where feasible path has a chance to work, we could just as well use enhanced feasible path because it is going to certainly improve upon feasible path. So the operational recommendation, if we look back at 84, I have been saying this all along. The recommendation, the way it is worded in the BCP 84 is that The mechanism relies on consistent route advertisements, that is the same prefixes through all the paths propagating to all the routers performing feasible RPF checking. And we relax that. So that's a bit stringent. All the prefixes must be announced and they must keep propagating up to all the routers that are doing feasible path as we move up from the customer to the core. We want to relax that as much as possible. And it's more words here, but it's actually a more relaxed or less stringent operational requirement. That is because all we are saying here is that if you are a multi-home stub AS, you must announce at least one of your origination prefixes without no export, or they should be exportable, unlike that example, to each of your transit providers. So at least one prefix exportable to each of your transit providers. And if you are a non-stub AS, you have some customers below. The above recommendation should still be applied regarding your origination prefixes, and additionally, for the transit routes that you have selected as best path, you must announce at least one route for each unique prefix origin pair to each transit provider. So a lot of words here, but hopefully these operational recommendations mean that this kind of anyway happens. It is natural for this kind of a behavior to happen, because all we are demanding is that at least one update should trickle up, right? We are not, only thing, what we are relaxing is that compared to BCP 84, not all updates are required to keep propagating up. At least one update in some sense in this definition, in this kind of a, with this kind of a principle should propagate up, okay? All right. So Jeff Haas has been very kind and helpful in terms of like discussing back and forth the implementation considerations related to this. So the main idea is that you do RPF checks in the line card, and in the line card you push the RIB into the line card, or some of the contents of the RIB into the line cards. And in the line card you have to look up the destination address once, and when you are doing your RPF, you also do a second lookup for the source address. So what are the source addresses that you are going to look for? That is what we were talking about, right? So those are the addresses that you need to say, okay, if the source address belongs to one of those prefixes, it's good. The data packet is good to go. If it doesn't, then the data packet is dropped. That is the idea of reverse path filtering. So as long as the demand on the RIB in the line card is not excessive, this has a, we could conceive of implementing it by enhancing the RPF in the RIB card. So if you do strict URPF, you have to have some additions, right, in the line card that says that the RIB tells me what are the destination addresses that are routable. In addition, if I do, for example, feasible path, those additional prefixes that are allowed in the source address, they are not coming strictly from the RIB. Some of them come from, I'm sorry, they are not coming strictly from the FIB, because they are not your best paths. So now we have sort of augmented that list by allowing some flexibility, and so those additional prefixes which are not necessarily tied to the RIB should also be included in the RPF filter list in the line card. So as long as that doesn't get too big and get too taxing on the TCAM memory or what have you in the line card, hopefully this has a chance. So we need to understand and try to think about that and see what are the implications in terms of the design of the line card and so on. So thanks, Jeff, for helping me a little bit there. So I think I'll let you look at this slide while I open it up for questions.
So Warren Kumari. My question's, I guess, somewhat about the last bit, the implementation bit. How much extra work is this? Is this basically just like another VRF with a sort of normal IP lookup and many possible, like, it feels as though this might be wildly expensive, but if not, it looks like it's a nice idea. Okay.
Eric Muller. So conceptually, this sounds kind of interesting, and I can see some potential good applications for it. As far as operational deployment goes, one really big concern I have with doing something like this is that, well, now I'm outsourcing my customer filtering to that customer's other transit providers, because any route they can leak through another transit, I'm now accepting from them.
Okay, one thing I forgot to mention along the way is, so you are doing filtering on different interface, prefix filtering. You follow the RFC 7454 or whatever. And now there is also RPKI and ROA origin validation coming along. So you're accepting these prefixes. The ones you rejected, they are out. They are not in your RIB. These are the ones that you have accepted. You have included them in your bus path selection. So at that point, you have done your prefix filtering. You may, down the road, you would have done your RPKI, ROA, origin validation. So you have a high degree of confidence that these prefixes are good. So that's the key.
Yeah, in conjunction with RPKI and all that, yeah, that makes sense.
Yeah, if bad prefixes get in, that we have to we are trying to prevent that.
Hi, Igor Wyszynski, Yahoo. The scenario that you described that doesn't work is actually incredibly common with content providers. There's a lot of us that set no export. In fact, we do that for our most critical prefixes like Anycast, GSLP prefixes.
Would you, when you say, let me ask you, when you set no export on all your, would you set no export on all your prefixes or maybe some?
Towards all but 2 ISPs, yes.
No export on all transit towards all ISPs except for 2.
Yes.
And no export on every one of the prefixes you announced to them, or some?
Some.
Some is good.
And or more specific, but
some or most is still okay. As long as there is at least one, this has a chance.
It is entirely possible that for a bunch of providers, it would be for all.
All of them.
Yes.
Okay, and in that case, the follow-up question is, if you put no export and you are saying I'm not giving you BGP, I don't want you to send the BGP update further along, would you want them to forward your data packets further along, or yes, only data packets only go up to them?
I would want them to forward my data packets. There are 2 directions, and the internet by nature is asynchronous.
Okay, so yeah, it would be nice to know like what percentage that is. You seem to be saying that you would announce some prefixes without no export. If that is the case, in most cases, we are still like good for those cases. So what percentage? So it will be good to know some statistics on that.
So percentage-wise, it's not a percent of prefixes. There are a lot of people that have really bad connectivity to some other people. In fact, there's a further scenario where it's not just no export, it's no export towards AS4.
Oh, specifically to
them.
Mm-hmm.
And that is incredibly common piece of traffic engineering that is being used.
Mm-hmm.
But if you have one prefix, sorry, never mind.
So all of them, again, yes, all your prefixes,
so,
in some cases, not in all.
So let's say, Telia, please do not propagate any of my prefixes towards Comcast, as an example, because your connectivity between you guys is bad. But it is entirely possible that I will send traffic towards Comcast on Telia. I just don't want it back.
Mm-hmm. Okay, so we need to, so feasible path, so feasible path wouldn't work, right? In such, and enhanced feasible path also has difficulties.
Right.
So I guess any of these, do you know if feasible path, anyone at all implements feasible path URPF?
Accidentally. By accident.
No, okay. But how about the strict URPF?
No.
Strict. Not common? Strict URPF, where you have a dedicated, where you have a directly connected customer, you know his prefixes.
I think there's strict URPF is implemented by eyeball networks towards the eyeball customers. specifically residential.
Mhm.
I don't know of anybody that is crazy enough to implement it towards their business customers.
Okay, so yeah, we're trying to help and see if BCP 84, so but the feasible path part of it has a chance. So
So I mean,
looks like it needs more.
there's another major blocker towards feasible path, and maybe I don't know this well enough, so correct me if I'm wrong. For people that run default route is a feasible path, right? Right. Well, it's excluded, but a lot of people rely on a default route being a feasible path.
No, default route is I mean, you're a customer, you're announcing your prefixes to your transit provider, but in terms of you're not taking the full table from them, you are default routing. So that is other direction. That direction doesn't matter here.
No, let me rephrase that. It is entirely possible that I will strip down the routing table that I receive from an AS and remove routes from it entirely because I also have a default route from them.
Mm-hmm. Yeah.
So if I do that, that means that these prefixes will not be visible on my adjacency towards that provider, and therefore feasible paths would break in that scenario. Therefore, feasible paths.
Oh, you are saying that the other updates that you need in order to do the common origin computation, those updates, you have thrown them out.
Correct. Yeah.
Okay, thank you for the comment.
Jeff, so Igor caught about 2/3 of the stuff I was going to say about where the routes get advertised. Long and short of it, sometimes the more specifics that BCP 84 would want you to send are not propagated for business reasons. Just simply, I don't want this network to be a transit for this traffic. So unfortunately, that piece of BCP 84 may not be deployable in some circumstances.
Yeah.
Others it might.
Other circumstances we can still consider. Is that what? Okay.
Right.
Okay.
It's something that it may help in some circumstances.
Mhm.
For the hardware stuff, there's sort of two broad sets of operations that most line cards tend to support that can allow these RPF features to work. The first one is obviously every line card has a destination lookup table where you can say this traffic goes here, and most RPF, either strict or loose, is basically taking the source, running it against the exact same table, and saying, if it's strict, do I have something that points the next stop off this interface, or potentially all the cards in your system are maintaining the same table with a subset of it actually saying this egress is this interface. So in terms of implementation, that's an easy one. If you're on a box that actually has specific lookups for multicast UPRF, that is another piece of machinery that can be taken advantage of, but it's usually a much smaller table. The problem we have here with going with the the enhancements you're talking about is we're looking to either extend one of these tables so that it gets basically additional noise from the perspective of its main use. So if we're using this for destination-based forwarding, and we're doing this for loose, and therefore we're including all the routes that are feasible on the system, and we want to group together additional things, that one may work, but to Warren's point, it has to go into sort of precious forwarding table entries. So if you're to take other presentations from Grow about where people are freaking out about the fib size expanding, well, this is intentionally increasing the size of the fib to allow this stuff to happen. So from a technical perspective, this is a way this could be done. But in terms of the impact on a implementation, what it would take to actually do this, it's fairly costly. And the problem is when you look at next generation line card features, they're usually looking a couple of years out in terms of the forwarding, and the firewall type features as well, they look a couple generations out. This would be the kind of thing that if this was to be a feature would have to get into people's roadmaps, and it would be many years before it popped out, and you'd have to plan for additional resources specifically for this purpose. So it's technically correct, could be done, has impact, may be deployable in some circumstances on existing hardware, but pervasiveness, especially at large transit providers, is probably unlikely based on the capacity.
You have to look forward and plan well ahead of time for this to come in maybe 5 years from now. So you have to give it enough time to plan well ahead. Let me just ask you one simple question. The better it works, the closer it is to the, how much time?
edges.
We need to close the queue.
Okay. The closer you are to the edge as opposed to the core, the better these things work.
Yes.
So considering that, wouldn't it be the case that your line, the additional load on the line card, because then we are dealing with much fewer prefixes that any particular AS might originate.
Mhm.
So the fractional increase in the load on the TCAM or the fib memory is smaller, right? As you move towards the edge, and that is where it is also most effective.
So you have the correct observation, but there's part of the life cycle of routers that you're not really accounting for that picture. The boxes at the edge also tend to be lower capacity because in many cases, today's edge routers, were at one point, yesterday's core routers. So sure, they have more capacity, they're able to deal with the edges, but they may have just enough capacity. Or in some cases, you may be buying much smaller boxes that just simply don't have a lot of smarts to them.
Yeah. So then you're back to the same thing about planning well ahead of time.
Right. You have to actually get this into a piece of the ecosystem that can accommodate it so that it can eventually work its way to the edges.
Okay. Thank you.
Job Snyder's entity. Let me first start with saying something kind. What I like in this approach is this is one of the first approaches where I see that somebody is trying to accommodate what happens in practice. Benefit of the doubt.
Thank you.
I think is a key factor in designing security mechanisms because it's either black or it's white approach clearly does not work in this problem space. So I like that as a philosophy, and I would encourage you to keep looking in such directions.
Thank you.
As to the specifics of this proposal, not only no export can be a challenge, but there is also many traffic engineering strategies where you, for instance, lower the local preference outside a geographical region, which results in the prefix not being exported within that region. So it's don't focus just on no export. Is everything related to traffic engineering can jeopardize this mechanism.
So not only no export, but also lowering of preferences.
Yes.
Did you say as it moves up towards the core or something?
For example, we have crazy BGP communities.
I'd like to understand more of that. Yeah.
I can show you offline.
Okay.
And there's a challenge of overclaiming because you compile a list of all the prefixes that are originated by an ASM. But in the cases of CDNs, a CDN might put a small cache in some ISP's network that only has a /24. But because the origin ASM is that of the CDN that is used globally, and the CDN may globally have up to a /9 worth of space, then that small ISP that has that small cache because of that single /24, traffic can be spoofed for the /9 that is owned by the CDN. And if you look at traffic spoof attacks, then the IP addresses are often randomized out of legitimately used IP space.
But you are good as long as the /9 is not announced in BGP.
Well, the totality of the /9 is announced from perhaps up to 3,000 vantage points. And that enables the one ISP to spoof quite some traffic. So what I see from that is that the inherent asymmetry between what you announce and what you actually send is a really tough challenge to solve.
Mm-hmm.
And I have no solution for that asymmetry.
So I appreciate the comment, yeah. So as long as we can, if we want to continue this work, for example, there are scenarios that we see where it is applicable and it makes sense in those scenarios for the ISPs to use it, maybe we can continue the work. But
yeah, if you can really nail down that if you use this in this scenario, there will never be any trouble, then then we can recommend for that particular style of deployment, this is a useful document. But we have to be, between the four of us, we identified a number of cases where it actually breaks things. So we need to make sure that that never happens.
Right. Thank you.
So Warren Kamari, kind of related to the last comment. Igor, I think for your sort of example where you're doing all your prefixes with no export, I think that you've fix this by simply announcing a sacrificial prefix, which then sort of closes the graph. It doesn't need to be the prefix you're actually using, but you can signal this works by announcing a sacrificial prefix.
I see.
And then, and then it fixes stuff and traffic still works, and you don't use that prefix for actual. It's kind of weird. Run away.
That's quite smart.
So yes, I can. However, that might expose my relationship with that ASN publicly, which is absolutely not what I want to do.
Some experimental prefix or something.
Well, so like Joe said, there's a lot of funky traffic engineering stuff that is done for business reasons. Some of it might be confidentiality. Is it literally that IS goes, we'll have a connection between you and I, nobody can know about it.
Mm-hmm.
That happens a lot in practice.
Okay.
Yeah.
So thank you for all the comments.
This is awesome. It'd be great to have, for example, on my network, I can run URPF because of a variety of reasons, and I would love to be able to. It'd be awesome.
Thank you.
Just a real quick comment, because what Job said really resonated with me. It's really important also to articulate where it will work, but what it breaks, Medica KO. So anyway, from Farside Security. But but articulating what it breaks, right, is as critical so that people actually know that, because some people just say, oh, it works here, well, maybe it'll work in my environment. But if you do articulate what breaks and why, that is also very important. Yeah. Love this draft.
Oh, thank you. Absolutely, what you're saying, I agree. So we have to focus on where it works, and we have to be, like others said, we have to be certain that it would work in those scenarios before applying this. Thank you.
You have to be very careful about third-party linkage. For example, if you turn this on, you will break your connectivity off.
Yeah, we need to stop the discussion here, for sake of time.
Thank you.
Thank you.
So this is Fernando again. Before I actually go through the actual contents of the IDE, let me try to introduce, how we came up with this document. I think years ago, I was working with some ICMP-based attacks that essentially were about spoofing ICMP version 6 packet-to-big messages, which trigger the use of let's say a weird feature in IPv6, which was atomic fragments. Okay, essentially you had two systems, that were transferring information with each other, and you could spoof one ICMP error message that would trigger the use of fragmentation. But as a result of the widespread dropping of fragments on the internet, that would cause those packets to get dropped. Essentially, you'd fire one single ICMP error, and that would cause, packets between the two endpoints to be dropped. There were many aspects to that attack. Like one of them was like, well, why do we have these weird atomic fragments in the first place? Which we took care about it. But the other one was a more generic one. Like, we have ICMP errors which don't even require the attacker to spoof the source address of the packets, because they could be coming from any router. So the idea was, well, what could some device that was at the very edge of the network do to try to prevent, let's say, users for launching this kind of attacks against other systems, okay? So we came up with this very simple filtering rule that needs to be applied at the edge, obviously not in cases in which you have multi-homing, okay? Because that's when things get more difficult. So now let's move to the, contents. So essentially the idea of what we are describing here is what you could do to filter or to prevent attackers at the edge of a network from performing attacks that require the spoofing of ICMP errors. Okay, there are many different possible attacks. The one that actually triggered this work was the use of packet-to-big error messages that again were triggering a specific case, the generation of atomic fragments in IPv6. But then there are other cases, like you could, for example, spoof ICMP errors that in some cases might, for example, cause connections to be reset, or other ones. Well, this one I mentioned has to be applied on the edge, and obviously not in cases where you have multi-homing. So as a brief refresher of how ICMP errors are generated, we have like two endpoints on the extremes. Let's say node A sends a packet, tries to send a packet through this router B, and let's say that message elicits an ICMP error. Essentially, the ICMP error will have a source address of the system that is sending the error. In this case, will be this router over here. The destination obviously will be the destination of the error message, which in this case is A on this side. The last pointer, yeah. And then the part that at times is tricky for people that are not into protocol, let's say internals, is that inside the ICMP error you put a piece of the packet that trigger the error message. So that means the original packet that was being sent from A to B or to D in this case. So this would be an attack scenario in which, let's say that we have these two systems that are transferring data. Could be a TCP connection or something. This could be the internet or some kind of like network over there. And in this case, we have the attacker. Okay. Now, what the attacker wants to do is to spoof an ICMP error, maybe in this case to this node over here, pretending that it came from somewhere here, from the path that the original packets were following. Now, when it comes to the source address, this one over here, the attacker doesn't actually need to spoof any address. Why? Because the error message could be coming from any router on the internet. Destination address will obviously be the target of the attack. Okay. The source address will correspond, to the system that originally sent the original packet. Now, the interesting part here is the destination address in the embedded packet. So you are sending an error message from here, and that essentially, when you look at the embedded payload, essentially this is implying that you got here a packet that was destined to this address. Okay. So if you don't have a multi-homing scenario, well, obviously you could have never actually received this packet here. So essentially what you do is something kind of like BCP38, but based on the destination address of the embedded payload. Meaning, if this address here doesn't belong to your network here, then that means that you shouldn't let the packet go through. Okay, you could have never received this original packet over here. The rule is essentially this, okay? Destination address of the embedded payload. If it's within my network, I will let the packet go through. Otherwise, I'll drop it. And obviously, again, this implies that you're looking inside the ICMP payload, meaning that in many cases you wouldn't, but in cases where you are looking inside or you can look inside, you might filter this. What are the changes that we apply on version 3? Well, first one was the original examples were IPv4 examples. Somebody said, okay, you should change that to v6. That's what we did. Then the second one is explain the possible limitations of inspecting ICMP payloads. And the third one, this was raised by Carlos Piñataro. In part of the ID, we have like the generic format for ICMP errors, but based on the extensions of specified in 4884, we had to. This is the ICMP extension options. We modified the the generic let's say syntax of ICMP errors to reflect the possibility of 4884. I don't know if there are comments and or interest on this.
So Warren Kamari, just a
Yes.
question. Do you know of any actual implementations that allow you to filter on the destination address inside the payload of currently?
No.
Okay. Okay, cool. Just checking.
Eric Link, just to reply to you, yes, I know at least one implementation doing it.
Okay.
And you can guess the vendor, right?
All the time works. Okay. Okay. Yeah.
I mean, yes, you wouldn't be doing like it can be expensive. So it's key where you would apply this. Yeah. I don't know if there are any further comments or people have looked at the ID or.
For me, it's an easy thing. So we should go and work in Glasscall for review and so on.
No, this one should be a call for adoption.
Okay, call for adoption first.
Yeah.
But
I mean, we can do last call if you want. If you. On the list.
on the list, yeah.
Yeah, cool.
Frank?
All right, hi. Presenting on behalf of a couple of co-authors, all of them listed here. And do you have a clicker or? There is a clicker. Okay. And we're trying to answer a question that, well, some people have that as top of mind, others don't have that much. We've been steering traffic for decades with traffic engineering, service chaining, policy-based routing, and whatever. Have we ever asked ourselves, is the traffic really following that path? I had that conversation, and actually the work was inspired by a gentleman called Steve Yule, now working at JPMC, those days working at another bank. And he said, well, I can't really do anything NFV. Because as soon as I virtualize, I lose the method that I'm using today to prove the path, which is probes and cable checking. And proving means showing to his management that all the traffic makes it through a particular set of firewalls. And well, sure, if you do an NFV, there's no cables, and a single misconfiguration of the vSwitch can go and mess the overall thing up. So how do we prove in a cryptographically secure way that traffic actually makes it through a set of, say, firewalls or whatever you consider? So problem domain is very easy. We're saying, well, we want to make sure that the traffic goes through A, B, C, and not A, X, C, and we want to be able to verify that it made it through that particular set of hops. I think that's the problem that we want to go solve. The approach that we took to that is, let's imagine we'd be able to have this Uber thing as a controller, and that controller would be able to have a secret, and that controller might be able to split that secret into as many hops as you want to see verified. That could be hops as a service chain. It could just be general routing hops that you want to make sure that the traffic is actually going through. So we're taking the secret, like the pie here, we're splitting that into as many hops as we have, and then at every single hop, we embed a piece of that secret, so that portion, into the packet as metadata. And then at the verification hop, we'll either be able to reassemble the pie, or, well, we're missing a piece of the pie, and hence it's not been through all the hops. Okay, simple concept. Obviously, putting the pie into the packet won't work, so we need something digital. And when we were shopping around for solutions, we ended up with two approaches. And the first one is to use Shamir secret sharing. So something that Adi Shamir came up with in 1984, I believe. And it goes back to school math, which is relatively simple from a concept perspective, because it leverages a polynomial as a secret. And if we remember school math, we all remember that a polynomial of degree n is defined by n plus 1 points. Line, 2 points, parabola, 3 points, cubic function, 4 points, and so forth. We all remember that, right? And it's uniquely identified by these points. Now, let's assume that we have a polynomial as the secret, and if we say want to verify 3 hops, we need 3 points, so we need a polynomial of degree 2. And these 3 points will one-to-one identify my polynomial. We give every single node, well, splitting that secret means we're giving every single node a point on the curve, and then the verifier would just need to go and retrieve the polynomial from these 3 points. Okay. All of that is, well, based on a mechanism that Adi Shamir invented, and it's, well, kind of feasible. But if you look at that mechanism, it would mean we need to go and create a secret polynomial per packet. That sounds like not too feasible, right? Operationally complex. But what we can do is just, again, think of what we learn in the school, which is if I have something secret and something public, the sum of something secret and something public is again something secret. That means we're not operating with one polynomial, we're operating with two polynomials and operating on the sum of the two. We're making one polynomial public and carrying that within the packet. And we're taking one that is secret, and we're always operating on the sum of the two. Now, you need to go and read through the draft, or I have a link to a presentation on SlideShare that goes and takes you through the math. But the overall thing can be done in a very computationally simple way. And we've proven that with a reference implementation in open source and VPP and Open Daylight. So it all comes down to every single node, including the verifier, would need to do two additions, one multiplication, and one division modulo a prime number. So there isn't a hell load of things that you need to go do because you're computing the Lagrange polynomials in a stepwise fashion. And the secret, to be dead honest, is not the entire polynomial. It's only the constant part of the polynomial. So it's just the constant number that we are retrieving. And again, as an identifier of the second polynomial, the public one, we're just using the constant number, so the constant coefficient, I have to say, in order to be, well, operationally easy here. What type of numbers would we need to go deal with? And I've just did a little bit of math. So if we are running, or if we're assuming that we're running at 100 gig, a 64-bit number, which is, well, the number of polynomials that we can have for the second polynomial, going back to the constant coefficient, we roughly can live with that for, well, 3,100 years, more or less, without reprovisioning the entire thing. If you say 64 bits of metadata that I need to go and carry, actually 2 times of 64 bits metadata that I need to go carry is too much. I only can carry 32. Well, this obviously goes down exponentially. Then you might need to go at 100 gig reprovision every 22 seconds. So there is a trade-off, but 64 bits, 2 times 64 bits sounds like a reasonable number. That's one approach. The downside of Shamir secret sharing is you are verifying that you've been through a set of hops. You're not verifying the sequence. That's actually something that Shamir secret sharing can't really do for us, given that the points on the curve are points on the curve. If we want to go and do something that is more like auto-preserving, there is a second approach documented in the draft that is more like composing an onion, which means you're taking a number and hop by hop, you're encrypting that number. So it's like you take the inner piece of the shell and then you're putting another shell and another shell, and the verifier would need to do the exact operation that you're doing through the network all itself. So you're step-by-step composing the onion as the packet traverses through the network, and the verifier would do the exact same thing. It wouldn't decrypt, it would just recompose the exact same thing. Obviously, if you compare the operational burden, the computational burden on this is far heavier. That said, there is chips out there that have AES chipset support. That means you have crypto chipsets out there that might be a feasible alternative to the other approach. So both of them are there. We've implemented Shamir secret sharing in open source. Well, that's just how you carry the data. I think that's not too interesting. We implemented the whole schema in open source, and an application that is in the Open Daylight Carbon release. So the controller who picks the secret and then splits the secret into as many nodes and hops you have, and we've implemented that as part of the service function chaining application in Open Daylight, communicates that along with the other parameters that you need, like the prime number, everything is done over a finite field. So everything is done modulo prime. So that's part of the implementation piece there. And the data plane implementation is done as open source and FIDO VPP, so on the vector packet processor. I've included the links to the documentation and also the code so that you can have a peek. It's also in a specific vendor implementation of that other vendor that I forgot the name of. Well, you can go and play around with that. If you're interested in the mathematics of that, the draft has a little bit of that. If you are looking for a nicer format, there is a presentation on SlideShare that takes you through how Shamir secret sharing works. So we appreciate commons and especially more of a thorough review from a security perspective, because what this does is obviously it's taken the packet through this thing and then kind of updating the cryptographic information. It's not really protecting the content. What we can do is the second random number as a packet identifier, we can use that as a hash across the entire packet. So it doesn't necessarily need to be entirely random. We can go and choose what we put in. But, well, there's obviously other concerns, and, well, I'd be interested to hear about those. And that leads me to the second question. Is that something like the problem itself, maybe not the solution that we have two, but the problem itself, is that something that Opsec is interested in looking into? Because, as I said, the gentleman from the financial industry, Steve Ewell, said, well, I have to stay with physical devices unless you solve that problem for me, at least for firewalls. Thoughts, comments?
That's what H is for.
May you want to go and... Ah.
That's what H is for.
Chris Morrow, Google. Jeff is saying that's what the H, the authentication header, is for in IPsec.
So Warren Kumari, I did look at this a while back and I've sort of forgotten. Don't you either need to do this over the whole contents of the packet or just accept the fact that somebody can replace the payload later and you still have proof that it went through it?
Yeah, correct. So I think that's the whole point. Like you can either, so the first incarnation of that document that we had was exactly like, you can swap the payload and the header's been verified. Yeah, check. You can link the payload to the metadata by providing a hash across the payload and, well,
in the header. Yeah.
By that way, ensuring that
okay. I just want to make
you're verifying that the content's been through that. That's where we are right now.
Chris Morrow, Google. How does this work for like cut-through switching and things like that, or do the people not care about the switch part of the path? Because the packet's going to be out the door before you can figure out what the hash of it was supposed to be. Right? There's a number of instances like this, I'm sure.
Yeah, well, I think it comes with certain deployment assumptions. We've been starting this effort purely, really, for the NFV problem, where we do believe that we have, well, control on the exit door, like a potential vSwitch or whatever. But, well, yeah, I think it comes with certain deployment constraints. And also, I think I've not seen a single chipset today that is able to do a modular prime operation efficiently in hardware. Software data plane like VPP, not an issue.
Eric Ving, Jeff, can I ask you a clarification question on your statement that because AH for me doesn't fill the requirement?
Jeff, so not the hop by hop requirement. This is specifically that this packet has been
touched by a specific box. Only that part.
We fully agree on this.
Yeah.
Sorry, Chris again. Jeff, why not just encrypt it, decrypt it, encrypt it, decrypt it on every hop of the network? Then you could see.
Or just stick multiple AH headers on the packet.
Yeah. No, question is this something that this working group is even interested in? So,
Igor Goshinsky, Yahoo, speaking for almost every hardware vendor that, because they're only capable of looking at 256 bytes of the packet. At some, yeah, I mean, at some point you'll majorly break every chipset out there.
no, but we didn't answer Frank's question. So think about his question for another 10 seconds and then come answer it.
Jean-Michel Combe. What could be interesting is not that this is the final point that could verify the path, but the origin element that could check the path, because this is the original point that wants that the flow goes through this point.
so you want some feedback from the verifier to the originator of the packet that his packet was delivered across the right path.
The way
well,
you want it.
Yeah, so it's seemingly, I think it's at least a problem that catches some interest. All right. All right. Thanks, guys.
With this, I guess it concludes the working group meeting. Thanks for coming. Everyone got the blue sheet, by the way? Okay. Yeah. It's this guy. Okay. Yeah, let's look at it.
So what I want to do with